So in this section, we're talking about the sampling distribution for proportions. In the last section, we talked about the sampling distribution for our sample means, our X bars. So now we're going to go through a very similar thought process, but dealing with proportions instead. So if we have binary qualitative data, remember qualitative is categorical, that only has two options, success or failure, we are going to summarize it with the proportion of successes. So if we're using proportions to summarize our population, then we have to code our data as X, each individual X value has to be a 0 or a 1. The 1 is the thing we want to count, the like yeses or whatever we're actually interested in. So our population parameter for our size, we'll do a capital N for our sample size, or population size. And the population proportion is you just add up all of the values and divide by how many there are. Because they're coded as zeros or ones, you can do it that way. And I'll show you why that makes sense in our next example. And our sample proportion, which we'll do as a p hat, is going to equal the sum of each X value divided by N. So on a previous example, we looked at the data for the pets that people have on my blog. So this table has the values I got for each of my pets. I'm going to recode each one as a 1 for dogs and a 0 for anything else. Now remember, this was for everyone on my block, so it is a very small population because it was everyone on my block, not just some people on my block. So if it's a dog, I'm going to say that the X value is 1. So all of the dogs, I'm going to put an X value of 1. Everything else is 0. So even though there were more categories originally, in this case, I only want to look at the people who have dogs. So everything else is just a 0. So if I want to find the proportion of people with dogs, I could have come up and I could have said there were 1, 2, 3, 4, 5, 6, like 1, 2, 3, 6 people that had dogs. And I think there were 15 people total. So my proportion is 0.4. So that's how we would have done it before we started figuring out how to recode our data. But now if we want to recode our data with ones and zeros, then my proportion, my population proportion, is just going to be where I add up all of the values and divide by how many there were. So I add up the 1 plus 1 plus 1, etc. And I get 6 out of 15 because basically every time there's something I'm interested in, we put a 1 there. And so when we add up those ones, we're just counting how many there were that we're interested in. So either way, we get to this 0.4 as my proportion. And really, the software is going to do all of that for you. So in our next example, Delta Dental had a third-party market research firm conduct a study. They surveyed 1,000 nationally representative U.S. families. So my population would be all U.S. families. The sample is the 1,000 families they actually surveyed. One question was if their children brush at least twice a day. They found that 72% of the families had children that brushed their teeth at least twice a day. So the observational units in this one is each family. So they only looked at each family. They didn't look at each person. So the units are the families. The variable they looked at is whether or not they brushed their teeth twice a day. Our sample statistic would be our sample proportion because it's a like yes/no question, so we deal with proportions when we look at it. And in our case, they told me what that is, so my sample proportion is 0.72. And the population parameter would be my population proportion, but they didn't tell me what it is because they don't have data on all the families in the US. So we don't know what it is, but it will be P. So now let's talk about sampling variability. Let's say we want to flip a coin 5 times and find out how often we get heads. We'll repeat this experiment a few times. So we'll come to this website where we can say we want to do 5 tosses. And I draw my sample. Okay. And you can see that I got heads, tail, 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 tail. So heads, tail, 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 tail. So if I was to rewrite these as X values, okay, we're interested in heads and nothing else. So my X values would be 1, 0, 0, 0, 0. My count of heads, how many heads did I actually get? I got 1. And so my sample proportion of heads would be 1/5, so 0.2. But if I did this again, I should get different results, right? So let's not keep seeing the animation. So the next time I get head, 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 tail, tail. So if I got 3 heads, or that would be 0.6 as a proportion. If I do it again, this time I got 5 heads. If I do it again, I got 5 heads. Do it again, I got 4 heads. So every time I'm going to get a different result. And we can fill out our table here. So on my second attempt that I recorded here, so a tail would be a 0, another tail would be 0, heads would be 1, heads would be 1, heads would be 1. So there were 3 heads, and my sample proportion would be 3 out of 5, so 0.6. The next time I got tail, 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 so that's 0, 0, 0, 0, 0. There are 0 heads, so my sample proportion is 0 out of 5, or 0. And my last attempt was head, 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 tail, head. So we'd have 1 every time we have a head, 0 for the tails, 1 for the head. So that gave me a 4. If you add up all those values, you also get 4, so 4 out of 5, which gives me 0.8. So the fact that we get different values every time we take a sample is called that sampling variability. And you can see we got very different sample proportions of heads when we're only flipping it 5 times. Now, it is always important to note that we can't predict our results on the next set of 5 coin tosses because they are random. Okay. But we can predict the overall expected value of all those possible sample proportions and describe how they will vary from sample to sample. That's the standard deviation. So let's flip the coin 5 times and then repeat that process 10,000 times. So I did this for us, and you can see my histogram for my 10,000 results. Notice as you look at this, it almost looks normal. Not super close, but it's trying to look kind of normal. So now, just like with means, we want to be able to predict our center and spread of the distribution of our possible sample proportions. So if we say that our sample size is n, and we have a population proportion of success p, then we find our sample proportion p hat by dividing our count by our number of observations. This is our formula we've been using. Now, using our linear combination formulas, just like we did for our sample mean, but I didn't put the proof in here, we can find that the expected value of all those possible sample proportions is equal to our population proportion. And the variance of all the possible sample proportions is equal to the population proportion p times 1 minus p over n. So if we flip the coin 5 times, and then we repeat that process thousands of times, let's describe the distribution of the counts. Okay, so first, the center, the expected value of p hat is supposed to be equal to p. Well, let's see. If we flip the coin 5 times, then my sample size is 5, and my population proportion should be 0.5 because it's a fair coin. We are assuming. So the expected value of all the possible sample proportions should be equal to my population proportion of 0.5. And to describe my spread, my variance of all the possible sample proportions should be equal to my population proportion of 0.5 times 1 minus 0.5 divided by n, which was unfortunately 5. That's a lot of 5s. Which gives me 0.05. And then the standard deviation is just the square root of that. So the square root of 0.05 gives me 0.2236. And so what does that tell me? That tells me that we can expect our sample proportions. When I go take a proportion, I can tell you it will probably be about 0.5, the expected value of p hat, give or take about 0.2236, which was the standard deviation of our possible sample means. Okay. So let's try another example. Oh, sorry, my computer's not. So in Utah, we know that of all the voters, so that tells you it's for the population, 50.55% are Republican. So when I see the word all, I'm going to make a note that that's my population. Okay. And so my population proportion is 0.5055 that are Republican. If we take a sample of 100 voters, so I want to take a sample and my sample size will be 100, what proportion would you expect to be Republican? Give or take what? Okay. So to do that, we need to say, well, what is the expected value for my sample proportion? That's just equal to my population proportion p, so 0.5055. And when it says a give or take, so I could skip doing the variance. That's usually an intermediate step. I could go straight to the standard deviation. which is the square root of p times 1 minus p over n. Make sure all of that is inside the square root. That's the biggest difficulty, putting in your calculator correctly. So we'll do the 0.5055 times 1 minus 0.5055 divided by n, which was 100. And it's about 0.05 if you round a bit. And so we could say that we would expect, in our sample, we would expect about 5.055 to be Republican, give or take 0.05. Let's see, we know that we're not going to get the same number of Republicans in every sample. Every different sample is going to give us different results, okay, which also means it's going to give us different sample proportions. So let's go back, or we can go back to our simulation. This is the same applet that we've been using. And if I make this a little bit bigger, I can come over here to and put in my population proportion. I know it says probability of heads. That's because they made it for coin flipping, but I'll do what I want. Every time we want to have a sample size of 100. Okay. So if I draw just one sample, okay, let's hide those spinners. You can see that, and I'll change it to proportion, you can see that I got a sample proportion of about like 0.38 or something. I could draw another sample. This time I got a higher sample proportion of 0.49. If I draw another sample, I got a higher one of like 0.53 maybe. A higher one of 0.43, another one of 0.45. So every time I'm getting a different sample proportion. Well, if I keep doing this, every time I'm drawing a new sample, you can see I get different sample proportions every time. Okay. Let's maybe draw a few more samples at a time. Okay. You can see that I just keep building this histogram. Okay, and as I draw more and more samples, it's starting to look more and more like a normal distribution. So let's draw maybe 1,000 at a time. You can see as I drew 1,000 more samples, it's starting to look like a normal distribution, and as I keep going, it's looking more and more like a normal distribution. These are all the possible sample proportions that I can get, or so far as all the sample proportions that I did get. So I did put one here on my notes, so that here's what the different proportions look like for 10,000 different samples, each of size 100. So the sample proportions look like they are normally distributed. Because they're normally distributed, we can use the normal distribution to find our probabilities. So let's find the probability that we pick a sample that has less than 40 Republicans. So if the sample has less than 40 Republicans, then that means we want to find the probability that p hat is less than, let's see, 40 out of remember my sample size is 100, so 0.4. So we want the chance that we get sample proportion less than 0.4. It's a normal curve, so we're looking for the 0.4, anything to the left of that. So we'll use p norm because it's a normal distribution. I'm interested in a p hat 0.4. I know that the mean, so we have to come up and see what did we find for our means. The mean, our expected value is supposed to be 0.5055, and the standard deviation is 0.05. So we'll put 0.5055, and then we'll use 0.05 as the standard deviation. And that should be something about like 0.0174. Now let's find the probability that we pick a sample that has more than 56 Republicans. So that would be p hat greater than 0.56 if you want to change it to a proportion. And if we want to sketch it out, we'll be looking for the right tail. So the probability that we get a p hat greater than 0.56 is going to be equal to p norm. I'm interested in the value 0.56. The mean or expected value is 0.5055. Standard deviation 0.05. And I want that right tail, so I have to do lower dot tail equals capital F. And this should give me something about 0.1379. If your rounding's a bit off, that's fine. Okay, so now let's discover our central limit theorem for proportions. Here's a few different examples where I had a population proportion where p equals 0.5. Notice even when I look at a sample size of 5, then these are my sample proportions. They look almost normal. So let's say that sample proportions, there's multiple ones. Each one is a different sample proportion. It almost looks normal. By the time I get to sample size of 50, it looks quite normal. By the time I get to sample size of 500, it looks very normal, right? What happens if I get a population proportion where p equals 0.1? If I have a sample size of 5, definitely not normal. It's still very skewed. Okay? At a sample size of 50, it's still skewed. It looks almost normal, but still skewed. But by the time I get to 500, it looks normal again. What if we try with a population proportion of 0.99? If I only do a sample size of 5, notice it is very much not normal. In fact, it's almost guaranteed to have everything to have a sample proportion of 1. Okay, definitely very skewed. But even at n equals 500, you're still kind of skewed. And notice that was 500. I changed how many I did here. But by the time I get to 5,000, it does look normal. So the shape of the sampling distribution of the sample proportions becomes more normal as the sample size gets bigger. But the question is, how big does our sample size need to be to use the normal distribution to estimate the sampling distribution of p hat? So the answer to that is it depends on the population proportion p is. Because if you come back up and look, when my population proportion was 0.5, even at a sample size of 5, we're looking pretty close to a normal distribution as far as the shape. By the time we get to 50, we look really quite good. But a population proportion of p equals 0.1, we had to get a much bigger sample size. Like we were up at 500 when it looked really good, like a normal curve. Okay, but if we had a population proportion 0.99, I had to go all the way out to 5,000. Even 500 wasn't big enough. Okay, and so it just kind of depends on what your original population proportion was. So what we're going to do is we're going to make the rule. We're going to check n times p. We're going to n times p and make sure that is at least 10. And we have to check n times 1 minus p is at least 10. The reason why is, like, if your population proportion was 0.1 and you did n times 0.1, it makes sense you want to make that at least 10. But if you did n times 0.99, it makes it feel like you don't have to have a very big sample size. But 0.99 is pretty big, but 1 minus 0.99 equals 0.01. And so that's the 1 minus p part. We need to check that that times n is at least 10. So we'll check both of those conditions. So let's summarize our sampling distribution for our sample proportion. The sampling distribution of all the possible sample proportions p hat for a sample size of n and a population proportion of success p, it will have an approximately normal distribution if n times p is at least 10 and n times 1 minus p is at least 10. It will have the mean, variance, and standard deviation with the formulas that we found. Okay. Now again, sampling distributions are important because knowing the sampling distribution for our possible sample proportions lets me predict how close my sample proportion for my actual data will be to the true unknown population proportion. So let's do some examples. About 20% of all U.S. adults with undergraduate degrees, have outstanding student debt. Suppose we want to take a sample of 50 adults. So write down what they told you. We have n equals 50. Now that 20%, they said that was for all the U.S. adults, so that sounds like a population proportion, not a sample. So my population proportion is 0.2. Now the sampling distribution of the sample proportion is, okay, let's figure it out. So is n times p at least 10? Okay, so we'll do 50, n is 50. We'll do 50 times 0.2, which gives me 10. So yep, we're good there. And n times 1 minus p is at least 10. So we'll do 50 times 1 minus 0.2, which gives me 40. So we're good there. Those are at least 10. If you look at it when I actually graphed it for you, you might see it is very, very slight skew. Okay, which makes sense because we were just barely at 10 when we did n times p. Okay, but it is close enough to use the normal distribution for approximations. It's close enough. So we can say that it's normal. Now we need to know our expected value of our possible sample proportions. That's just always equal to our population proportion p, so we'll say 0.2. And the standard deviation of p hat is the square root of p times 1 minus p over n. So the square root of 0.2 times 1 minus 0.2 divided by 50, which is 0.057 if I round a bit. So if I want to actually write this out, I would say p hat is distributed normally with an expected value of 0.2, and a variance of 0.057 squared. You can figure out what 0.057 squared is. Often we'll just write it like that because we know we really care about the standard deviation for all the rest of our formulas. See, so I would expect a sample of 50 of the U.S. adults with undergraduate degrees to have a sample proportion of about 0.2, give or take 0.057, that have outstanding student debt. So now, what is the chance that I pick a sample with between 0.16 and 0.24 people with outstanding student debt? So it's asking, what is the chance that we get a sample proportion between 0.16 and 0.24? So we'll write that as 0.16 less than or equal to our p hat less than or equal to 0.24. Okay, to do this, we're going to need to use p norm because we said it's a normal distribution. Here's my 0.16, here's my 0.24. I want the area in between them. So remember, we have to do p norm of the bigger value minus p norm of the smaller value. So we'll do p norm of 0.24, comma, and then we put our expected value of 0.2. We put our standard deviation of 0.057 minus, we'll do p norm again, and we put in our 0.16, expected value 0.2, standard deviation 0.057. This should give me, see, the first probability is 0.7586 minus, and then the next one is 0.2414. So this should give me 0.5172. So that's the chance that we could pick a sample with between 16% and 24% of people that do have outstanding student debt. And I can ask you, approximately 95% of all of the possible sample proportions are between blank and blank. Okay, so we know from the empirical rule that if you have your expected value, here p hat, and you go out one standard deviation in either direction, that should be 68%. And if you go out two standard deviations either direction, that should be 95% of your data. So 95% of all the possible sample proportions should be within the expected value plus or minus 2 times the standard deviation. And I want to make sure I use expected value for p hat, standard deviation for p hat. So we'll do 0.2 plus or minus 2 times the 0.057. And that should give me 0.087 to 0.313. So 95% of our possible sample proportions will be between those two values. So this one is we're going to do a statistical investigation from start to finish with our whole process. So if you're talking about ESP, that's when people know things that they shouldn't be able to know. So in one experiment that they actually put in a research journal, a subject was asked to guess the card out of 5 choices selected by a researcher in another room. The subject chose 557 cards correctly out of 850 cards. First, ask a statistical question. So the question is, does the subject have ESP? And we're going to measure that by, can he guess the correct card more times than what we'd expect if he was just guessing? Step 2, collect the data. They ran the study. He chose 557 out of 1850 correct. Let's change that to a sample proportion. We'll say p hat equals, so we'll do 557 divided by 1850. P hat is 0.3. So are his results just due to chance? Could he have chosen 557 or more correctly if he was just guessing? Or is something happening besides him blindly guessing? So what proportion would you expect him to get right if he was just guessing? They said he had 5 choices. So if he was truly just guessing, we would expect it to be 1/5. Now, what proportion of the guesses were correct? We said he got 0.3 correct. So what's the distribution of the sample proportion if the guesses were just random? Let's see, let's label a few of these things. So if he was guessing, we'll say if guessing, then my population proportion should be 1/5 or 0.2. And he got a sample proportion of 0.3. So now what would we have expected him to get if it was random? So we would expect the sample proportion, the expected value of the sample proportion would be equal to p, so equal to 0.2. And the standard deviation of p hat would be equal to the square root of p times 1 minus p over n. So the square root of 0.2 times 1 minus 0.2 divided by n, which is 1850. So we get 0.009. And we should see what is the shape. Would it be normal? So let's check n times p. So 1850 times p of 0.2. That gives me something much bigger than 10. Gives me 370. And if I do n times 1 minus p, that's 1850 times 1 minus 0.2. So 1480. Both of those are bigger than 10, so it's normal. So we know the shape, we know the center, we know the spread, that's our distribution. So now I can ask, what's the probability of observing a proportion at least that big of what we actually got if the subject is just randomly guessing? So what's the probability that we would get a sample proportion greater than 0.3 if he was just guessing? So if the population proportion is really 0.2. So we're going to do p norm. Let's draw our picture. So here's my 0.3. We're looking for the area to the right. So we'll do p norm. We're interested in 0.3. Our expected value is 0.2 if he's guessing. The standard deviation is 0.09. And because I want the right tail, I'm going to do lower dot tail equals false. You can type out the entire word false or just the capital F. So let's get, when I put it in R, I get 5.54 times 10 to the negative 29th power. So in R, when I run it, this is what it looks like, the 5.538, and then it's e to the negative 29. That's what it means as a scientific notation. So it's 5.54 times 10 to the negative 29. So that is a very, very small chance. So there is a almost impossible chance that he could have gotten a sample proportion of 0.3 if he was truly guessing. So then we want to draw our conclusions. So do you think he was randomly guessing, or do you think he has ESP? So let's go ahead and write something like that. So if he was guessing, there is about a 0% chance that he could have gotten 0.3 or more correct. Okay. This sounds almost impossible. Okay, I really don't think he was randomly guessing. However, the study could be flawed. He could be cheating in some way. So either he has ESP or somehow the study was flawed. Okay, but there's no way that he did that just by guessing randomly. Now, could you generalize this to all people? No, we only had data on him, so it would only apply to him. So he was the only person in our study, so it only applies to him. Now, again, our calculations just tell us that it was incredibly unlikely that he was just guessing. The calculations can't actually tell you if the study was designed well. You should always look into the details of any study. Perhaps he was cheating in some way. Don't just blindly trust the results of a study.